Hi, and welcome to the first video for General Chemistry 1. Today I want to tell you why the same force that can cause your pipes to burst in the winter can also keep you from being cheated into buying fake jewelry. To get there, I want to go way back, to medieval times. Back then, the science of chemistry hadn't been developed yet. Instead, we had alchemy. Today, we remember alchemy mainly because alchemists were searching for things that we now know just don't exist, like the Philosopher's Stone. The Philosopher's Stone wasn't a kind of rock you might find in the ground. Instead, it was a substance that was supposed to be able to turn base metals, those are non-valuable metals like copper or tin, into gold. The Philosopher's Stone could also be used to make the elixir of life, which could grant you immortality as long as you kept drinking it now and then. Alchemists spent literally hundreds of years searching for a way to make the Philosopher's Stone, and of course it never worked, but that doesn't mean their time was wasted. In order to perform experiments, they had to invent a lot of the lab equipment that we use even today. Florence flasks, Erlenmeyer flasks, beakers, and some of the more complicated equipment that you'll use when you take organic chem were all invented by alchemists hundreds of years ago. So alchemy wasn't useless, but it wasn't what we call a science today. Why not? Well, for a lot of reasons, but the main problem was that alchemists weren't very methodical. They'd often repeat each other's work without realizing that what they were doing had already been done before. This was because they were pretty secretive. If they did make that Philosopher's Stone, they didn't want someone else to steal their discovery, so they usually didn't share notes. And when they did write about what they had tried, it was in such flowery language that it was hard to figure out what they had actually done in their labs. Today, we take a much different approach in science, and we can sum it up in what's called the scientific method. Take a look at this short clip from the movie Rosencrantz and Guildenstern Are Dead.
This is interesting. You would think this would fall faster than this, wouldn't you? And you'd be absolutely right.
This is actually a pretty good illustration of a few steps in the scientific method. The first step is the easiest. Make lots of observations. You already do this yourself all the time. Notice things. Keep your eyes and ears open, and sometimes you'll notice something interesting that you can't explain. That's what Guildenstern's doing as he's tossing things out of the chest. He notices that something heavy and something light seem to fall and hit the ground at the same time. The heavy one doesn't fall faster. The next step is one that usually doesn't get mentioned when people talk about the scientific method. You have to think hard. This is a crucial step that poor Guildenstern skipped in the movie. Think hard about your observations. Take your time. Try to imagine the reason for the things that you saw, and don't limit yourself to just one explanation. Think of as many different possible explanations as you can. Try to take everything you can think of into account. What are all the different things that could cause what you saw? This part should be fun. It's a chance to be creative and imagine what's going on. Maybe you'll come up with an explanation that no one's thought of before. Once you've come up with as many different explanations as possible, pick the one that you think is the most likely. That's going to be your hypothesis. It's your best guess at explaining your observations. Once you have a hypothesis, you're ready to do experiments. You design an experiment to test your hypothesis and make a prediction about how the experiment will turn out if the hypothesis is true. Guildenstern did do that. If your experiment gives negative results, it might mean your hypothesis is flawed, and if so, it's back to the drawing board. If you're lucky, the results of your failed experiment will help you make a better hypothesis. That's why you spent so much time coming up with as many alternate hypotheses as you could before. With luck, eventually one of your experiments gives you a positive result. That means you get to do more experiments. One single positive result is almost never enough to make a scientist satisfied with their hypothesis. Instead, we have to do more experiments. We try to find as many ways as possible to poke a hole in the hypothesis. Basically, we're trying to make the hypothesis fail. Only when we've tested it in as many ways as we can think of do we decide that it's good enough to share. And at that point, we announce our result. Now other scientists will be able to read about it, and they'll try to poke holes in our hypothesis too. They'll do experiments of their own to try to make the hypothesis fail, not because they're trying to embarrass us or trip up our good idea, but because we all want to be as sure as we can be that the hypothesis is correct. Eventually, if our hypothesis has been tested hundreds of times and passed every test, maybe it'll become part of a theory. And now would be a good time to go over a couple of definitions that people sometimes mix up. First, hypothesis. As I mentioned before, a hypothesis is a tentative explanation for a phenomenon that we've observed. An important thing about a hypothesis is that it has to be possible to think of an experiment in which the hypothesis would be proven wrong. If it's impossible to imagine a way an experiment could disprove the hypothesis, then it's a bad hypothesis. So for example, suppose I notice that some trees nearby are dying. I can come up with a lot of different hypotheses why. Maybe they're not getting enough water, or there might be a disease affecting them. There could be a toxic chemical in the soil, or maybe there's a beetle or other insect harming them. All of those are decent hypotheses because we can test them. For example, we could gather soil samples from around the trees and analyze them to see what chemicals are in the soil. If we don't find anything harmful, then we discard that hypothesis. On the other hand, I could hypothesize that an evil spirit has cursed the grove. That's a bad hypothesis because there's no experiment we could do that would disprove it. How could you prove that there's no such thing as a curse? The other word I want to define is theory. A theory is an explanation that has been tested many, many times and passed every test, so it's an explanation that we have a lot of confidence in. But more than that, a theory has to explain many different phenomena. So for example, germ theory. That's the idea that diseases are caused by microscopic organisms. It's a theory because it explains many different phenomena. Why diseases occur, how they spread, why disease treatments work, and so on. This is true for anything we call a theory. The theory of general relativity, the theory of evolution, atomic theory, all of these get called theories because they help explain many different phenomena. I mentioned atomic theory a second ago. We'll talk a lot more about it in future videos, but for now I want to mention a few things from atomic theory that will be important in the next few lectures. When we talk about matter, basically that means anything that has mass, and matter can be split into a couple of different categories: pure substances and mixtures. Let's take pure substances first. Every particle in a pure substance has the same composition. If you reach in and grab two random bits of a pure substance, they'll be made of exactly the same stuff. Now there are two kinds of pure substance. First, there's elements. You've probably seen the periodic table before. It's a chart of all the elements that we've discovered so far. Right now, there are 118 of them. Any given element always has the same composition, so that makes elements pure substances. Most elements can exist as single atoms. For example, helium and carbon can exist as single atoms of helium or carbon. These are known as monatomic elements, meaning one atom. On the other hand, there are some elements that are always paired up. For example, oxygen gas is made of paired oxygen atoms, O2. Single oxygen atoms aren't stable by themselves, so oxygen is called a diatomic element. There are 7 diatomic elements I want you to know about for now. Fortunately, they're pretty easy to remember. One is hydrogen. We can't have single plain hydrogen atoms. They're not stable. Instead, they pair up to give us H2 molecules. The other 6 diatomic elements I want you to know are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These make a group shaped like a 7 up in the corner of the table, which hopefully makes them easy to remember. You should make an effort to remember the diatomic elements soon, because they're going to come up in class a lot, starting in the next couple of lectures. Okay, back to the kinds of matter. Elements are one kind of pure substance, the other kind is compounds. Compounds are made of different elements. For example, water is made of 2 hydrogens and 1 oxygen, H2O. Pretty simple. The other type of matter is mixtures. Unlike pure substances, mixtures don't always have the exact same composition. For example, 2 different classes of salt water could have different amounts of salt and water in them. That's different from a pure substance, which always has the same constituents in the same amounts. Just as with pure substances, there are 2 different kinds of mixture. In a homogeneous mixture, the composition is uniform throughout. For example, in a glass of sugar water, the ratio of sugar to water is the same everywhere in the glass. It's uniform. That makes this a homogeneous mixture. On the other hand, in a heterogeneous mixture, the composition isn't uniform. A good example of this is fresh milk. Fresh milk usually has a layer of cream on top, so the composition at the top of the glass is different than the composition down here. It's a heterogeneous mixture. That's why when you buy milk in a grocery store, the label says it's homogenized milk. The cream has been blended in so that, unlike fresh milk, it's homogeneous, it's uniform. Okay, now we can finally get to the question I mentioned at the very beginning of the video. What's the connection between your pipes bursting in the winter and being able to tell real gold from the fake stuff? The answer has to do with the Greek philosopher Archimedes. Around 300 BC, Herod II, king of Syracuse, commissioned a gold wreath, which he was going to place on the head of a statue of a god during a ceremony. He thought the goldsmith might have cheated him by making a wreath that was actually silver with gold mixed into it to give it the right color. It would have been sacrilege to damage the wreath in order to determine whether it was pure gold or not, so he asked Archimedes to come up with a way to test it without damaging the wreath. The story is that Archimedes went to think it over while taking a bath. When he got in his bathtub, the water level rose and overflowed the tub, and he suddenly had the idea that could prove whether the wreath was gold or not. First, they'd weigh the wreath, then put it in a bowl and fill the bowl to the brim with water. Then they'd take the wreath out and put in a bar of pure gold that weighed the same amount the wreath did. If the water came up to the same level, it would prove that the wreath really was made of solid gold. If not, then the wreath was fake. That's because an impure sample of gold would take up a different amount of space than a pure sample would take up. Today, we'd say the property that Archimedes was using was the gold's density. The density of an object is its mass divided by its volume. So, for example, let's say that the wreath weighed 715 grams. That's its mass. The density of gold is 19.3 grams per milliliter. If we plug these 2 numbers into the equation for density, we can figure out the volume of the crown. Hopefully you've had a little algebra, so you know that in order to solve for V, first we multiply both sides by V, and then divide both sides by 19.3. That gives us our volume, 37.0 milliliters. Density is also what makes your pipes burst. Ice has a lower density than water, so if you have water in your pipes and it freezes, look what the equation tells you is going to happen. Ice has a lower density, so D is going to decrease when the water freezes. But the mass doesn't change, so M stays the same. In order for the density D to decrease, when M is a constant, V is going to have to go up. So, the ice is going to take up more volume than the water did. As the ice expands, its volume increases, and it pushes out on the pipes, and the force is so great it'll rupture even a heavy water pipe. We'll work with density a lot more in class, but for now, that's all I need to tell you. I'll see you in class soon.